Hey y'all, it's Kat. We're gonna be doing video homework assignment 1. So we're starting off with the function f of xy equals 5 minus 2x squared minus 2y squared. Right now we're just thinking about it 2D because we only have 2 variables, but I know this gets into 3D, so it's gonna be a paraboloid, and we know that it's gonna be upside down rather than like a bowl because of our negative x and negative y. But part A, we're calculating a vector perpendicular to the level of the curve of f at the point -1, -1, and draw the contour diagram at that point. To start, we're going to take our function and find the partial derivatives for x and y. We do that by just taking the derivative of each just with respect to the variable that we're looking at. So for f of x, we have -4x, and for f of y, we have -4y. Then, to find a gradient vector, we are going to plug in the point -1, -1 into each of those to get their result. So both of those are 4 because when we plug in -1 times -4, 4. And our gradient vector of f is going to be 4i plus 4j, and once again this is the vector perpendicular to the level curve at that point. I went ahead and did part B as well on the contour diagram by plugging in points into the original function. I started off with the original point that we're given, -1, -1, and got our result, which is z. So that's equals 1. So we're going to find that point on the graph and then put it on the contour diagram that has the steepness of 1, which is again our z output. And the arrow of that is going to be pointing towards the origin because it's where f is increasing the fastest. Also, that's if you saw it in a 3D way, it'd be pointing towards the peak. And then I did 3 more points, 1, 0, 2, 0, and 3, 0, and each of those outputs are the depth of the contour line. So I also labeled those on our XY graph because X and Y are inputs. The contour diagram lines are our Z, which is our output. So those are shown on there. I kind of drew them not spaced well, but you get the idea. So like I said, I already did B, which was plugging in 3 different level curves into that original equation. Part C asks to calculate a vector perpendicular to the surface when z equals f of xy at the point -1, -1, 1, and then sketch this and show the direction of the perpendicular vector. So in order to turn our 2D graph into a 3D graph, we're basically just going to set f of xy equal to z. So we take 5 minus 2x squared minus 2y squared equals z and set that whole thing equal to 0. So now we have our vector perpendicular to the surface, which is f of xyz equals 5 minus 2x squared minus 2y squared minus z equals 0. We're going to find gradient of that by taking the partial derivatives of each of those components to the x, the y, and the z. I did that right below. And then we're going to plug in the point -1, -1, 1. So we have our values of 4, 4, and -1. That's going to be our vector at the point -1, -1, 1. I went ahead and drew the 3D graph of this, which is, again, the vector perpendicular to the surface. This is the surface plot at the point. So I calculated for the radius, and it's the square root of 2.5, so that's going to be in between 1 and 2. And we also have our point, again, perpendicular to the surface. It creates right angles with the contour graph or diagram. And that's at the point -1, -1. And it's going to be pointing upwards once again towards the point of greatest increase of the function. And that's also the peak. Now for part D, we're going to compare our contour diagram and our 3D diagram. We see that I drew little contour lines with the red dash on the right diagram. that represent the lines that are in the 2D graph. So same thing, but just in a different dimension. And we see that as the circles on the contour diagram get smaller, we're rising, we're going further towards the peak of the graph. And both of the arrows on here are pointing in the same direction. Just once again, we have another dimension added on the right hand graph. So it's going to be going upwards rather than just inwards, but they both point towards the peak. Part E I did just touch on a little bit, but it's asking for the relation between the gradient vector f of -1, -1 to a vector tangent to the path at the point -1, -1, 1 that points uphill. So the point -1, -1 is directly above the point -1, -1 on the contour diagram. Again, just changing dimensions, but same idea. So the lines on the contour diagram are our z, and we see that as we get further or have greater x values and greater y values, when we're looking in the positive direction for both, our z or our output is getting smaller. So we see that the z is going to get more negative as we move further away. The gradient vector f, -1, -1 lies in a 2D space, and it points toward the peak of where f increases the most. Both vectors do point in the same direction, and the gradient vector lies directly below the vector tangent to the path at -1, -1, 1. Lastly, for part f, we're looking to find the vector n that's perpendicular to the surface, and the vector t tangent to the curve of the steepest descent, which is perpendicular to n. So we did find n in part C. It's the gradient of uppercase F, and that's just -4xi plus -4yj plus -1k. We're going to plug in that point, -1, -1, 1, into our gradient, and we're going to get our vector n as 4i plus 4j minus k. In order to find t, it's going to be the same thing, but we don't have a value for a, or the constant that goes in front of k. So we're going to replace that constant with the letter a for the time being. In order to find a, we have to take the dot product of n and t. So that's just multiplying the i, the j, and the k components in order to find a. So once we go through that simple algebra, we find that a is 32, and we can plug it back in so that we get a vector t of 4i plus 4j minus 32k. That should be all, and I hope that this explanation makes sense, because it does to me. So, yeah.